In example 114, we're going to find the mean and standard deviation for the sampling distribution of sample means that we worked out in example 113. I've included it here so we don't have to rewrite it. And since this is a discrete probability distribution, we can actually find these values by using the formulas from chapter 5. Now, on the previous page, we introduced some formulas saying that mu sub x bar, the mu of the sampling distribution of sample means, would be equal to mu of the population, and that the standard deviation for the x bars was equal to the standard deviation for the population over the size of our sample. Now, what we're going to do is find these values using our chapter 5 formulas, and then we'll compare it to what we get if we use these formulas, and we'll take a closer look at the original population to help us do that. So to begin, let's find the mean for this sampling distribution of sample means. We need to take the sum of the x bar values times the p of x bar values. So I'm just giving a little bit more space on this table to help organize the work here. Now I've already put in my calculator, I put the x bar values in L1 and the probability values are in L2. And so I'm going to have my calculator help me out with this. I'm going to have it put the x bar times p of x bar values in L3, and I'm going to have it put the x bar squared times p of x bar values in L4. So stat and edit. There's my x bar values in L1 and the probability values in L2. I'm going to have it put the x bar times the probability values in L3, so I'm making sure that L3 is highlighted. If it's not, I'll arrow up to it. And now I just tell it to calculate L1 times L2, and there are my values for the x bar times p of x. And I'm also going to need the values for the x squared times p of x, so I'll have my calculator put that in L4. So making sure L4 is highlighted, I select L1 squared times L2. And so now we have our table filled out. The mean for our x bars will be given just by taking the sum of my L3 column right here. So I'm going to have my calculator help me out with that. I'm going to quit to home. And now I'm going to hit second stat, arrow over to the math menu and select sum. I wanted to add up the L3 column, and I get 4. So the mean for the sampling distribution of sample means, u sub x bar is equal to 4. And now for sigma, for finding the standard deviation, we're going to first find sigma squared. And we're going to need to add up the L4 column for that. Going to add up the L4 column to figure out what goes right here. So second stat, math menu, selecting the sum, and telling it to add up the items in list 4. We get 20. And of course we have to subtract off mu squared. Of course this is mu of the x bars squared. So minus 4 squared. 4 squared is 16. 20 minus 16 is 4. So we have our standard deviation. The square is equal to 4, which means that sigma x bar must be equal to 2. So there's our mean and standard deviation for this, the distribution of the sample means. Now let's take a look at what we would get by first examining what mu and sigma are for the original population. Here's our original population. So it's the sort of an unlimited number, we'd say, of each of these digits that we could take. Remember that when we made the samples of size 2, we could take doubles, right? So what we're going to do is not think of making a frequency distribution, but a population probability distribution. And so I'm going to list the x values and then the probability that each of them have. Now they each have an equally likely chance of occurring, 1 out of 5 or 0.2. So that's fairly simple to fill in. So now let's find, this is P of x, not P of x bar. So now let's find mu and sigma just for this population probability distribution. Not for the x bars, but just for the straight up x values. Using the same formula in chapter 5. And let's see what we get. We get a mean of 4. And so here's something we could just observe right now. The mean of the sampling distribution of sample means we found up here is equal to the population mean. Just as the formula on the previous page that we were introduced to claims that would happen. So we've sort of verified that. Let's sort of seen it with our own eyes. Now let's find the standard deviation for this population. So we're going to use the formula to find sigma squared. All right, so each of the squares of each of the x values times their probability gives us 24. And then subtracting off square of the mean. 4 squared is 16. 24 minus 16 is 8. And so sigma here is the square root of 8. Or approximately 2.828. So now let's compare this value. Remember the formula that we were introduced to on the previous page about finding sigma sub x bar said it would be equal to sigma over root n. So let's figure out what is sigma over root n, and let's compare it to what we got above. So the sigma we found, our population standard deviation is right here, the 2.828. Over square root of n, and that's the size of the samples in our sampling distribution. So we took samples of size 2, so 2.828 over the square root of 2. So divide this value we just got by the square root of 2, and we get 2. And so looking up here, what we did, that's precisely what we got when we calculated the standard deviation for the sampling distribution of sample means. So I wanted to go through this kind of example just to sort of see for our own eyes that these formulas do hold, and for a situation when it is actually possible to take all possible sizes of a given size. So in the examples to come, and when we are using these and seeing these some more, we're actually just going to take advantage of these formulas here that we just sort of verified in this example, and we won't have to go through it using sort of these longer formulas to use from chapter 5.